Thank you for the introduction. I'm Do-Kyung Song, a PhD student at UC Irvine. I'm going to be talking about our work, Periscope, an effective probing and fuzzing framework for the hardware OS boundary. This is a joint work between UC Irvine, TU Berlin, UC Santa Barbara, KU Leuven. Today, the security of peripheral devices remains questionable. As has been demonstrated by security researchers, peripheral devices such as Wi-Fi chips that expose an interface to the external world can be compromised over the air by just sending maliciously crafted packets to the device. One of the enabling reasons for such an attack is that peripheral devices are typically resource constrained, and they lack basic defense mechanisms such as data execution prevention that make writing exploits more difficult. After compromising the peripheral device, the attacker is faced with what's called hardware OS interface. Just like OS kernels protect themselves from user space adversaries at the boundary of system core interface, at this boundary of hardware OS interface, OS kernels protect themselves from peripheral devices that could potentially turn malicious. Among others, there are two popular mechanisms of implementing hardware OS interface: memory mapped I/O and direct memory access. In memory mapped I/O, the device and the driver communicate with each other by writing to and reading from device registers. In the case of direct memory access, they communicate with each other by writing to and reading from physical memory pages shared between them. By compromising this hardware OS interface, the attacker can effectively turn a peripheral compromise into a full system compromise. In our work, we aim to analyze the security of this hardware OS interface operating under the following threat model. We assume that the attacker has compromised the peripheral device and can write any values to device registers and physical memory pages shared between the device and the driver. By analyzing the hardware's OS interface, we aim to find vulnerabilities in the drivers that can be triggered and exploited by the attacker on a compromised peripheral device. So what are the state-of-the-art and available tools that can analyze this hardware OS boundary? We first find a dynamic approach which adapts or reprograms the device such that it can send malicious values to the driver and examines driver's response. While non-intrusive and can be OS independent, there is a need for device-specific effort, which needs to be duplicated for each and individual device. And also, there's limited visibility into the driver. The second approach we find, which is also dynamic, is a virtual machine-based approach, where the analyst runs the entire system, including the device and the driver, on a virtual machine or a hypervisor. While a virtual machine provides convenient mechanisms to interpose the execution of its guests, it requires virtual device implementation and or CPU's hypervisor support, which can be problematic because in many cases, virtual device implementation is not available, in which case the analyst must implement it. Even if they can implement it, the implementation may not actually capture the behavior of the actual device. The third approach we find is a symbolic execution-based approach, which removes the need for devices altogether, and instead it replaces the I/O mappings with symbolic variables. It inherits, though, the downside of symbolic execution. For example, it may not scale well to a large device driver because of the fundamental path explosion problem. Our approach is an in-kernel dynamic approach, which does not require any change on the device side, nor does it require the system to run on a virtualized environment. We take a page fault-based monitoring approach to interpose the interactions between the device and the driver. This allows us to examine, also potentially to influence the traffic between the device and the driver at a fine-grained granularity, all within the kernel. Here's the overview of how Periscope works. When the device driver allocates either MMIO or DMA mapping, we mark the allocated pages as not present by modifying the corresponding page table entries in the page table. We do so by hooking into kernel's standard MMIO and DMA APIs. When the device driver later accesses these MMIO or DMA mappings, page fault exceptions will be triggered, which transfers the control into the kernel's page fault handler. And we hook into the kernel's page fault handler to call our page fault handler, in which we examine the fault and call user-registered hooks, which can be implemented for a wide variety of analysis purposes. Then it transfers the control back to the driver to resume its normal execution. Based on this framework, we built Perifuzz, a fuzzer that enables adversarial analysis of the hardware OS boundary. The goal here, as I mentioned, is to find vulnerabilities in the driver reachable from a compromised device. Therefore, Perifuzz fuzzes drivers' read accesses to these IO mappings because the values being read by the driver can be under the attacker's control under our threat model. So to this end, Perifuzz implements a custom hook that is registered with the Periscope framework. Whenever there is a driver's read accesses, Perifuzz hook requests fuzzing that read access that's being made. The injector component of Perifuzz receives input generated by the fuzzer running in user space and injects that fuzzer supplied value to the destination register of the faulting instruction. Then it resumes the driver's execution from the instruction that immediately follows the faulting instruction. The same procedure repeats for each driver's read accesses until the injected value leads to any observable error in the driver, such as segmentation fault. Let me quickly review our threat model in more detail. Since peripheral device and the device driver each runs on a separate processor operating on their own clock, the attacker can not only write any value to these IO mappings, but also at any time, even multiple times, and potentially in between drivers' read accesses. This gives rise to the potential presence of double fetch bugs in IO mappings. Double fetch bugs are a class of time of check to time of use race conditions. Let me give you an example. On the right-hand side, the device driver is about to fetch a value from an IO mapping and compares it with hex value FF. Because the fetched value is indeed less than FF, the control is transferred into the basic block protected by the check. After passing this check, peripheral device makes a malicious update to the bytes that were just fetched by the device driver. And then the driver performs an overlapping fetch of the exact same bytes. And at this point, the fact that the driver has passed the if condition check is no longer valid, and also subsequent uses of this value might lead the system to an exploitable state. For example, a potential buffer overflow in this example. With this in mind, we designed the following fuzzer input consumption model. So the idea is to sequentially consume the bytes in the fuzzer-generated input to provide a different value to each fetch, regardless of whether the fetch overlaps with any of the previous fetches or not. Let me give you an example. Given a fuzzer-generated input, the device driver fetches 2 bytes from an IO mapping, for which Perifuzz consumes the first 2 bytes available in the fuzzer-generated input. And then the device driver performs an overlapping fetch of the exact same bytes, for which Perifuzz consumes the next available 2 bytes from the IO mapping. Of course, if there is a non-overlapping fetch, Perifuzz also consumes the next available 2 bytes from the fuzzer-generated input. To explain how all of this fits into a bigger picture and eventually form a fuzzing loop, let me just quickly review how device interrupts are handled by the OS kernel. So Linux kernel's interrupt handling can be broadly subdivided into top half and bottom half handling of interrupts. Because most of the work is done by bottom half handlers, we aligned the fuzzing loop to one of the bottom half handler mechanisms called software interrupt handler, or soft IRQ. At various points in time that the kernel finds it convenient, the kernel calls software interrupt handlers registered by the device drivers. We hook into the entrance and the exit of the software interrupt handler, and then we switch the fuzzer input after the exit, and an execution of a software interrupt handler corresponds to a single iteration of the fuzzing loop in which the bytes in the fuzzer generated input are consecutively consumed according to our fuzzer input consumption model. We based our prototype implementation on Linux kernel version 4.4 for the ARM v8 architecture, which was used in the earlier versions of Google Pixel 2. We ported that to kernel version 3.10, which is used in Samsung Galaxy S6. We used AFL as peripheral fuzzer front end. In our experiment, we targeted two Wi-Fi drivers used in popular Android smartphones, Google's Pixel 2 and Samsung's Galaxy S6. Let me explain a few key properties of this target to highlight the stringent requirement that they put on any analysis effort. First of all, they are among the largest in terms of the number of source lines of code. Both drivers consist of more than hundreds of thousands of lines of code, and they are also highly concurrent, making heavy use of bottom half handlers and kernel threads. And also, lots of code runs in interrupt and kernel thread context instead of system call context, which means that existing driver fuzzers that target the system core interface cannot directly fuzz these code paths. Also, to our knowledge, no virtual device implementation is available. And finally, production phones typically do not expose the EL2 privilege level to the end user, so hypervisor-based approach cannot be directly applied here to analyze these drivers. We found 15 vulnerabilities in total, among which 9 were previously unknown. 8 new CVEs were assigned. We found different classes of bugs, not just most common vulnerabilities, such as buffer overflows, but also more subtle memory-related vulnerabilities, such as double fetch issues and kernel address leak. We also found several reachable assertions and null pointer dereferences, which could impact the availability of the system. Let me describe two subtle bugs we found in this talk. So double fetch bug started with the driver initially fetching a message from an IO mapping for an integrity check that verifies the checksum of the entire message. Once this message passes the integrity check, the driver proceeds to process the message, and unfortunately, the driver fetches the same bytes again from the message, which is later used as an index into an array, which caused the system to crash. Let me also describe the kernel address leak we found. The symptom, as we encountered, was that the driver was directly dereferencing the value provided by our fuzzer. After a quick investigation, we noticed that a kernel pointer was being disclosed in the first place to the device in the name of cookie, and the device uses that value internally and writes that back to an IO mapping, which is subsequently read and dereferenced by the driver. Perifuzz fuzzed the cookie value when the driver was reading that value, and subsequent dereference of it caused the system to crash. Here's the performance of our system in terms of the fuzzing throughput. The fuzzing throughput ranged from about 7 to 24 inputs per second, and it depends on the I/O mapping that's being fuzzed. So the primary contributor of this fuzzing throughput is the number of page faults incurred within each iteration of the fuzzing loop. We expect an improvement of at least 2 to 3x with further optimization, the details of which can be found in the paper. Just to put these numbers into perspective, although it cannot be directly compared, we ran syscaller on the same device and achieved 24 program executions on average with a maximum around 60. We see these as a future work. We expect to find more bugs by minimizing the impact of shallow bugs and also improving the throughput in general. We frequently hit shallow bugs, and which caused significant delay in fuzzing because each crash caused about 1 minute delay. So we had to manually disable several code paths rooted at the bugs that we already found. But this was only a limited manual effort. We can also improve the throughput because it is slower than, for example, what one would expect in fuzzing user space programs. As I said, possible optimizations and different design that makes a different trade-off is discussed in the paper. To conclude, remote peripheral compromise poses a serious threat to OS kernel security, as evidenced by 15 vulnerabilities we found in our fuzzing experiment. Periscope and Perifuzz are practical dynamic analysis tools that can analyze large, complex device drivers along the hardware OS boundary. And these tools are also effective at finding vulnerabilities along the hardware OS boundary. With our tools, we found not only memory safety violations, but also other subtle memory issues, and also several reachable assertions and log pointer references. With that, I'd like to thank you all for your attention, and I'm happy to take any questions.
First is, did you measure the code coverage in terms of line coverage or instruction coverage?
Yes.
Yes, so how is the coverage?
We did not perform actually exhaustive measurement, but in my experience, the coverage was actually a little low because of the shallow bugs that we frequently hit. So most of the bugs were found within 10,000 iterations, which means several minutes of fuzzing.
I see. So roughly how many live code, how many % of the code is covered?
I don't have that number, actually.
OK, thanks. Yeah. So the next question is, did you see any timeout caused by your page fault handling-based inputs? I'm
sorry, did you see what?
So you use the page faults. You mark the buffer and MMIO as non-accessible, and they access them trigger the page fault. So does it cause any peripheral timeout? Because some operations are time sensitive, and the page fault handling is
didn't get the, does it cause what? I'm sorry.
Did you observe any timeouts?
Timeout?
Yeah, peripheral.
Yes, we did observe some timeouts, but there was a configuration parameter when we were compiling the kernel for these Android devices, and we increased the delay a little bit.
OK, thanks.
Yeah, Eric Pauley, Penn State. As kind of a follow-up to the previous question, did you basically use AFL's black box mode in order to do the fuzzing since you didn't have coverage instrumentation? And then do you think that it would be made more effective if you added some sort of coverage instrumentation?
So yes, we actually modified AFL a little bit, but we actually found that coverage-guided fuzzing is not really fully effective because of the accumulating states. Actually, internal states accumulate, and the same input does not lead to any, like the same path, does not follow the same code path when provided at this point and at another point.
So when you did those experiments with coverage guided, how did you go about instrumenting the coverage? Did you actually instrument the driver?
Yes, that's in the paper. You can find that in the paper because the current implementation of KCOV does not actually support tracking the coverage of the interrupt handlers and kernel threads or something because it was originally tailored to fuzzing system call interface. So yeah, we kind of modified that to track the coverage from the interrupt handler.
Okay, thanks.
Hi, Malachi Jones, MITRE. The question I had is that you guys found like double fetch bugs, and so I was wondering if the fact that you, like first person asked, the fact that you had latency delays with the page faults, that could have contributed to those double fetch bugs, right? Because you're adding more delays, so it's a better chance for having that double fetch bug to happen. So I was just wondering if you guys thought about that, and how did you account for that, or how likely is it that that contributed to those bugs being found?
How likely is it that we can find double fetch bugs?
Well, no. How likely is it that the delay that happens when you do the page fault, right? So there's like latency delay that you add when you do the hooks. So I'm saying, how likely is it that those delays allowed you to contribute to the race condition that you're able to find for getting the double fetch bugs? So what I'm saying is the more you increase the delay, the more likely it's possible, the more likely that you can find more double fetch bugs. And so I'm wondering, how did you guys handle that?
I don't think our approach depends on any of the timing, like, issues, I guess.
Well, you said that like
Yeah, we are delaying actually the execution of the driver, but we are kind of deterministically tracking every access, and just the fact that the driver is making two different accesses at different points in time, that could constitute actually a double fetch bug if the fetched IO mapping is shared between a privileged entity and non-privileged entity. In this case, non-privileged entity is the device.
Okay, thanks.